blockchain labs. We were the initial builders of Arbitrum, but we also are continuously supporting Arbitrum as a DAO on the research and development side. And one of the most exciting new technologies we have to offer to the Arbitrum ecosystem is what we call Stylus, which is our new WebAssembly VM. And I'll get into that and explain a little bit more about that. But yeah, just wanted to kind of give you a high level of what I want to cover during this talk. I'm going to kind of give you sort of a high level introduction to Rust. If you know any programming language existing, if you just know a little bit about it, you don't have to know all of Rust in order to be productive with Stylus. So I'm going to cover enough to get you productive with it, and then kind of explain like a basic example. And then I think Jose, after me, will go more in depth on a more detailed example. Okay, so with that, let's move on. Just to kind of reiterate what Stylus is. Stylus is a new virtual machine execution environment for Arbitrum blockchains, and it works off of WebAssembly technology. That means any WebAssembly language is supported technically. Primarily, right now off the bat, we're kind of supporting traditional systems languages like C, C++, and Rust. But there's a lot of niche languages like AssemblyScript and Zig, and many other WebAssembly languages that can be supported. There are certain nuances with with that, but you know, to start off with, we've kind of built out a very robust Rust SDK. So that's what I'll be covering on this talk today. But just note that Stylus is not limited to Rust. It's just our primary target to launch with. So some of the benefits of Stylus is that it allows up to 70 times more compute versus a standard smart contract, and it allows 1,000 times more memory to be accessed for the same amount of gas during a transaction. At the same time, it remains composable with EVM, so you can call Solidity from Rust, and you can call Rust from Solidity. You can call C from Rust, and vice versa. You know, so it's very composable, and it works with the existing Ethereum ecosystem. So it should fit nicely once it rolls out to Arbitrum mainnet. Some of the other, you know, high-level benefits of Stylus is that, you know, when you're using a language like Rust, you get access to like general purpose language tooling, because Rust is used in a much more broader context outside of smart contract development. So you get access to a lot more tooling, bigger libraries to pull from. So it definitely, you know, we're trying to tap into a lot of the brilliant open source work that's being done in all these other ecosystems, and bring that into smart contract dev, and kind of modernize smart contract dev a lot more compared with like what you get with Solidity, which is a special purpose smart contract language. Other benefits of it, like with different programming languages, you get different coding paradigms. Maybe you want to code in a functional language, you code in a language like Haskell or something, you find a way to compile it to WebAssembly. You could work with it like that, but just other patterns just kind of exist in Rust by default compared with Solidity that you're more than welcome to use in your code. It also helps us as a ecosystem onboard more developers from Web 2, because they may have more experience with these more traditional languages like C, Rust, Go, Java, etc. You know, these types of things that we can more easily support languages that are either quite similar to those or precisely the ones that they're already using, and onboard devs through that. We also, you know, we want to access the broader dev ecosystem. There's, you know, millions of devs that are outside of smart contract development, so it helps us to onboard those developers more easily. So just I kind of covered this in the document. Like if I think Jason and others at the conference were sharing this document about installation prereqs on your laptop. So this slide is just sort of like reiterating some of that. If you get lost at any point, refer to our docs at docs.arbitrum.io. And if you click the Quick Start Rust under the Stylus section, it will help you get your environment set up and kind of reiterate, maybe more detail than what's on that on the document we shared. If you get stuck at any point, just go to docs.arbitrum.io, and everything that I'm about to tell you is located there as well. Also, yeah, when you want to develop a smart contract, it helps to run a local development environment, which we call local dev node. That's also under the Stylus docs, and it also included instructions on the FOSSASIA instructions. So again, hopefully you've got maybe your local dev node set up if you want to follow along. But yeah, the example that I'm going to show you later will be run on my local machine, but you're also welcome to deploy to the public Stylus testnet, which is located at stylustestnet.arbitrum.io/RPC. But for that, you would need Sequoia E. So I'm not going to get into that much. We'll probably just work with the local dev node. But if you have any questions on that, feel free to definitely ask Jason. He's there in the conference to help you. So he can definitely help you get set up. Okay, so moving on to like Rust. I'm going to, again, kind of give you some high level details about Rust, enough to get productive with it, enough to like write a basic contract with it. So some of the primary advantages that Rust has, maybe over other languages, that it's a very strongly typed language, it's memory safe. This comes in handy a lot of times when you're doing like systems level programming, but in smart contract development helps a lot too. The compiler tends to prevent a lot of mistakes that would kind of sometimes accidentally be made with a language like Solidity. It also has like a lot of high level features, while it's as fast as almost as fast as a language like C. So you get access to a lot of modern programming language features from maybe something that you're used to from Java or Go or one of those, but it's as fast as C, so it's very good for both smart contract dev and just general systems level programming. The compiler is also, it will give you very detailed warnings, so it can a lot of times catch many mistakes and things like that that you can learn from the compiler as you're learning Rust itself. So it's very descriptive in the errors and very helpful in that sense. It's got other cool features like powerful pattern matching. I might be able to cover a little bit of that later, but just to give you a couple of the main benefits of why Rust. Okay, so I'm going to kind of cover variables and mutability, just like high level, to explain to you that by default, variables in Rust are immutable. That means they can't be overwritten after being declared unless they were explicitly declared as mutable. So if you see over here on the top box here, it shows that this doesn't compile, where I'm just assigning the value 5 to the variable X. And then afterwards, if you try to overwrite that variable, the compiler will throw an error as soon as you try to compile it. But to fix that, if you want to be able to mutate a variable, you see in the second example below, I'm just saying let mute X equal 5, and then assigning 6 to that variable, which, again, I'm just declaring that variable mutable, and then that lets the Rust compiler know that, okay, this is mutable from this, after this point. And it helps with like things like ownership and determining whether a variable should be allowed to be overwritten or not, if somebody else is expecting that it won't change. This is not details that you have to worry about that much, but it's important to note that to declare a mutable variable, you use that keyword. Okay. So these are some of the primitive data types that are available in Rust. You've got access to, unsigned integers, signed integers, all the way up to 128 bits. So here you got 8, 16, 32-bit, all the way up to 128 bits. And then you've got this special type called usize or isize. And those variables are just basically going to, usize or isize is just sort of a keyword for whatever environment you're compiling in, whatever its default or max size is. A lot of times you're going to be compiling in a 64-bit environment that might be, default to U64. WASM itself tends to use 32-bit values, so usize, if you use the usize keyword, it's probably going to be a U32 in a WASM environment. But you don't need to really use these usize. It's better to just explicitly declare what size of the variables that you want. So these are the primitives that are kind of available to you. And then below here on the integer literal section, kind of see like these different ways of declaring different types of numbers, like decimals, hex values, binary. And notice how the underscores are kind of ignored. So like that decimal value that says 98_222, that's just 98,222. The underscore is just ignored. It's just there for like to kind of visually break up large numbers so that it's easier to read. But yeah, just a couple of little syntax details about Rust. Other data types that are available to you are, of course, booleans. So here where I'm saying let f bool equal false, that's just saying this is a Boolean type. And then let me make sure that my audio is working. I want to make sure that I'm okay. Thank you. All right, I just got an error message. Okay. So you can use you can declare Boolean types. You just use that colon syntax to indicate the type. Character types, tuple types. So tuples, if you need to do more than one type at a time and kind of group it up into a single variable, you can use tuples. So I'm just using let tup, and I'm using that parenthesis syntax U32 comma bool, and then I'm assigning it that integer that follows the 500 and the true, and that those values are both available in that tup. But you can have n number of tuples. You can have 10, 20 elements in a tuple. You're not limited to just like 2 elements, for example. And then that's a standard array. Should look very similar to array syntax from many other languages. Following with this is how you define functions in Rust. You just got the fn keyword followed by the name of the function. And you see 2 functions here. Notice another function, the second function on this list is using snake case. That's a default in Rust, is to declare functions with that snake casing, which is just using the underscore separator instead of like traditional language. A lot of languages you will use like camel casing, where the second word is the first letter is capitalized. Rust tends to use, at least for functions, it'll use the snake casing style. Continuing on with functions, if you want to return a value, you use this arrow syntax if you want to return a value from a function. So if you see that this +1 function on the right, I'm passing in an I32 as X, and then I'm adding 1 to it, and I'm returning an I32. So it's just, you use that arrow syntax to return it. Very simple. You can also return more complex types like tuples or structs. And then you just name variables, just like parameter with the X colon, that's the name of that variable. Also, one note is that, notice on the +1 function, when I'm returning X + 1, I'm not using a semicolon there. And basically by default in Rust, if you don't use the semicolon, that is the return value for that function, if that's the last statement in the function. So X + 1 is implicitly returned there, where it just knows, since that's the very end of the function statement, that it's going to return that X + 1 as the return value for I32. You don't have to like type out return unless you want to return early, like inside an if statement or something like that. You can explicitly type out the return, but otherwise it's just implicit returns. Okay. To define different types of data, if you want to structure, group certain types of data together and kind of provide like named fields, like this rectangle here, we've got the width and height. and the types are defined. So you kind of just, it's sort of a schema for data, and you just declare structs. This is a rectangle with the width U32, height is a U32, so 32-bit integers for the height and width of this struct. And it's very similar to like objects in existing like object-oriented languages that you're probably used to, but there are subtle differences to note with structs. It's just, you know, and I won't get into that in this talk. It's just, but like you can kind of think of structs as objects, but they're somewhat different. And I think you'll learn that as you go. But again, I kind of just want to teach you the minimum to kind of understand these examples that we're about to explain to you. So for now, you can kind of think of them as objects. Moving on here, if you want to declare, like if you want to declare an instance of a rectangle, for example, in this main function, I'm just saying let rect1 equals rectangle, and I'm using the curly brace syntax. And then I'm instantiating a rectangle here with width 30 and height 50. So very simple syntax to use to declare an instance of a struct. That might be different than like in an object-oriented language. A lot of times you'll use this new keyword. Rust by default does not have any like new keyword defined for instantiating like structs. So, you know, you just kind of use this named syntax with the fields. And if you, you know, you can optionally declare methods on it if you want, but this is the default syntax for instantiation. If you want to define a method on a struct, which is, again, maybe analogous to defining a method on an object in an OOP language, use this impl keyword, IMPL. So notice how I've defined the rectangle up at the top with the width and height. And then below that, I've got an impl rectangle. So again, I'm just repeating the name of the struct here. So impl rectangle, I'm just repeating the name of the rectangle struct above. That's going to let the compiler know that any instance of a rectangle has access to the methods defined inside this impl body. And so here I've defined an area method. It has this like syntax called and self, which is that is a read-only reference to itself. Again, might be similar to OOP languages where maybe you're using this or self in OOP languages. So it's very similar. The key thing to note here is because it's it's kind of this ampersand, which is a reference to self. That means it's an immutable reference. That means this method is going to be a read-only method. So the fn area is an area method. It's going to return a U32, and it's just computing the area, which is the width times the height. Okay. Moving on from there, Rust also has access to enums. So you can define enums. Here's an example where I'm defining a coin enum, and I've got penny, nickel, dime, quarter. These enums don't necessarily have values attached to them. So in this case, there is no value really attached. Like a lot of languages will assign like maybe, you know, 0, 1, 2, 3, 4 by default to these enums. In Rust that doesn't happen unless it's explicitly attached. So in this case, these values sort of just kind of only exist at compile time. These enums here, just something to note. So how you might use this. This is an example of how you might use an enum. Basically, I've got a function here where I'm passing in a coin, using an enum as a type. So I'm referring to that coin type when I define the coin parameter that's being passed into value and cents. And then I'm using this cool feature in Rust, which is a match statement. And I'm matching on that parameter. And then I'm using this coin : : syntax to define all the arms of what a coin might be. So a coin has to be either a penny, nickel, dime, or quarter based on this definition above. So Rust compiler also makes sure that you define every possible when you use a match statement like this, you have to define like a branch for every possible enumeration or every possible pattern that it could match. There is a syntax that you can use to kind of use a catch-all if you don't want to define it for everyone, for every single option. But the compiler will let you know, if you're missing something. So it's just something to keep in mind. And then, yeah, this is just a match statement that's returning an 8-bit integer based on whether it's a penny, nickel, dime, or quarter. So very simple function, but pattern matching in Rust is a very powerful feature. You don't have to understand all of that or what that means, but as you get to know Rust, you'll see what I mean. These are some examples of maybe some more like complex, like kind of control flow. This is like 2 alternate ways to do the same code. So right here on the top, I'm defining this config max variable, and I'm assigning it this sum, which is a type, and then I'm passing in this an 8-bit integer. That 3U8 means it's an 8-bit unsigned integer, and it's the number 3. So I'm passing in the config max value. Now has the value, like in the first line, has the value sum 3, and then the match statement below that, where you're looking at match config max, that first branch is saying, well, if it is some value, then print the line the maximum is configured to be that max. Okay, these 2 boxes are equivalent. This is just 2 different syntaxes for writing the same thing. You can either like first assign it to a variable and then match on that variable, or Rust also has this like sort of like shorthand syntax of doing the same thing, where you do this if let statement, and it's if let if the max, basically like if config max, this if let will only run if it matches that initial branch, which is sum max. Okay. And then it will print the line next to it. Yep. And then, okay, moving on. So Rust also has this system called traits, which are very similar to interfaces that you might find in OOP languages. So this is just kind of defining behavior or expected behavior that should be defined for a given struct if you want to implement that trait for a given struct. You can also implement traits for enums, but it's just something to keep in mind. So this is just defining a super basic trait, where I'm saying that if a struct has the summary trait, then it must have a function, a method defined on it called summarize that returns a string. So that's just very, very similar to interfaces. But it can also kind of have some properties of like abstract classes and stuff. But again, not something to worry about when you're just starting off. Think of them more like interfaces for now. This is an example of interfaces in practice. So we've got this tweet struct that's defined above, where we've got a username, content, reply field, retweet field. Okay, so these are just a couple strings, a couple booleans, just to define a quick struct to kind of give you a basic example. And then if I want to implement summary, again, this summary trait means that I have to, for a struct to implement this trait, I have to define the summarize method. So that's what we're doing over here on this slide. We're implementing. You can kind of think of that impl as meaning implementing. We're implementing summary, the summary trait, for the tweet struct. And then below that, we're defining this summarize method that actually has the concrete implementation, where it's formatting. It's just returning a string where it just concatenates the username with a colon, username and content with a colon in between it. So pretty basic trait there and implementation there, but you kind of get the idea where we define this behavior, and then we made the concrete implementation for the tweet struct here. Okay, another important thing to know about Rust that you'll come across a lot is this concept of macros. Macros are used in lots of features, We've already seen a couple of them here where this print line, for example, you've seen in a couple of these examples or format, exclamation point. When you see that exclamation point at the end, like here on this print line statement, when you see that, that means you're invoking a macro. And then the arguments that follow it are being passed to that macro. But there's a couple different types of macros. You see the second line, the hashtag, derived, debug. Again, you don't, because I'm just trying to explain the beginner Rust details, you don't really need to fully understand what's happening here, except that when you invoke a macro, ultimately, like when you hit compile, it's going to generate code under the hood that does this more complex behavior that you don't need to really understand at first. You kind of just, high level know, okay, print line is taking these strings and it's figuring out and it's writing some code underneath the hood to kind of put out to the console, and to fill in like wherever you got these curly braces, to fill in the name string there, for example, as the first, So it's just doing complex behavior under the hood that happens at compile time. It expands your code using a macro context. If you've ever used any other programming language with the macro feature, you'll get it right away. But if you haven't, that's okay. Just understand that under the hood, it's doing complex advanced behavior to expand your code to make it more complex to achieve something in a more terse way, or like to find something in a very short way without having to write a bunch of boilerplate code, So it's just something to keep in mind. They are fully programmable. You can make your own macros. They're very, very powerful. They're also very advanced feature of Rust and very complicated to build. So you don't need to know how to build them off the bat. Just kind of know that when you're invoking with this exclamation point or using this hashtag syntax, your code is using macros under the hood. And the Stylus SDK uses these macros to like simplify development, to kind of prevent you from needing to write a lot of boilerplate code. So just something to keep in mind. Okay, now I'm going to start kind of covering more of the SDK itself and kind of go into these details about how you might begin to write a smart contract in Rust, and just kind of give you what our high level goals with the SDK were and continue to be. We're going to be continuing to improve on the SDK, but we do operate in an Ethereum EVM dominated context. So even though Stylus is much more powerful than the EVM, the EVM has probably 7 or 8 years of legacy in the Ethereum ecosystem. So there's lots of existing smart contracts that are written in Solidity. And, we want to remain fully compatible with all that. So part of how we designed the SDK was to make sure that we were fully compatible and that contracts could be supported back and forth between Rust and Solidity, and that you could, devs could easily kind of understand it if they're coming from that Solidity background. If you're coming from like a Web 2 background, you may not sometimes understand why the Rust SDK maybe is referring to Solidity, but it's important to note that because of the Solidity legacy in the Ethereum ecosystem, we have to remain compatible. So sometimes you'll see things like you might see some syntax that's slightly different inside of a Stylus contract, and usually it's using a Solidity macro to make something simpler to define in Rust that might be have been ported over from an old Solidity contract or something like that. So to help with that, we're using a library called Alloy, which is a Rust library that makes it easier to do these like type conversions between Rust primitives and Solidity primitives, because there's a difference in the standard primitives that come with Solidity and the standard primitives that come with Rust. So it's just a library that helps us do that. So you'll see some of those conversions in the code examples coming up, but just something to keep in mind that, like Solidity as an example, just as one of the basic examples, is Solidity works off of 256-bit integers almost by default. whereas like Rust currently doesn't have native support for 256-bit integers. You have to use a library to get that kind of support. Right now, it currently only supports up to 128 bits. So things like that, like converting between, you know, these 256-bit values, 256-bit values, and, you know, local Rust primitives. The Alloy library helps with that. Just something to keep in mind. Yeah, again, it's all about composability and maintaining cross-contract functionality. Okay, so when you, if you set up your environment, if you follow the FOSSASIA instructions that we've handed out to you, and if you've got Cargo Stylus installed on your system, you can run this command, which is Cargo Stylus new, and then you can name your contract to be whatever you want. You can call it My First Contract or whatever you want to call it, Hello World, whatever you want to call it. And what it's going to do, Cargo Stylus will create a folder with a couple of files in it, and it'll just set up everything you need to get like a basic contract going. And I'll show you that live in a second. But if you want to test this out in your terminal, you're welcome to do that. But I'll show it to you live in just a few minutes. Once you've got your like basic contract set up, you can kind of CD into that folder. You can run this command called Cargo Stylus check, and that CLI command what it's doing is it's going to make sure your code compiles, and it's going to make sure that your program is less than the maximum size that Stylus supports. So currently we support a maximum program size up to 24 kilobytes, but the Cargo Stylus CLI tool will let you know, it'll try to compress your code and it'll try to shrink it down as much as possible in order to fit it on chain. Currently those aren't parameters that we necessarily set ourselves. We're following the Ethereum EVM standards with that size limit. So your contract does need to be less than 24 kilobytes. If you need more than that, after compress, you can write multiple contracts and kind of split your logic across multiple contracts. It's usually how that's handled in smart contract development. But it's something to keep in mind. 24 kilobytes is not a lot. It's you want to be mindful of the size of your programs and the dependencies that you bring into your code. So it's just something to keep in mind. On-chain resources are quite a bit limited compared with like operating in a desktop environment or like web environment. So it's something to keep in mind. When you want to deploy your code, you'll call Cargo Stylus deploy. Right here, I'm on this example, you'll see I'm invoking -e flag, which is the endpoint flag, and I'm using localhost 8547, which is a local dev node. If you follow the instructions and you've got a local dev node, you can deploy contracts against that using this argument where you do -e, and the localhost 8547 is the default port that the Stylus dev node deploys to. And then this -- private key path, you basically will use what's called a private key to you'll paste that into a text file, and I'll show you an example of that, because when you deploy a local dev node, it will create a development account, that's standard development account for everybody, and it has ETH loaded on it. You need ETH in Arbitrum chains, you need ETH in any kind of Ethereum chain in order to deploy contracts, and in order to invoke any state changes in your contract, you always usually need ETH. And so in order to spin ETH, you need a private key of an address that contains ETH in order to spend ETH out of that account. So just kind of something that, understand, just kind of follow along these instructions. If this doesn't make sense to you, I think it will over time, but like for now, you can just like note that you need to pass in either a private key path or private key in order to execute on-chain changes. Okay. More high-level details about the Rust SDK. These are some primitive value types. Again, this is using that alloy library that I was talking about before that allows for the solidity compatibility. Expands primitives to 256 bits. Like I said before, Rust by default only goes up to 128 bits. So that's part of the benefit of the library. The other thing is that data is encoded in a different way in Solidity versus Rust. I don't know how far along you are in your education, if you know what big Indian is versus little Indian. There's differences in Rust defaults and Solidity defaults there. So this library helps like encode things properly. So you see here where I'm saying the first line 2 there, I'm just saying let 8-bit. It's a U8. I'm using this capital U8 here, which means I'm pulling that U8 primitive from the alloy library. If you looked at my dependencies above this is just like the inline example, but I'd be pulling that capital U8 dependency from the alloy library. And then over here on the right side of the equal sign where I'm saying U8 : from 1, that is saying create an alloy, a 8-bit alloy primitive from the number 1. So it's going to just create an instance of an alloy primitive U8 8-bit integer that has the value 1. And below that, like I'm defining a 256-bit integer, but instead of using the standard decimal syntax, I'm using a hex style syntax with that 0xFF, and I'm using a 64-bit integer to pass it in, but it's instantiating it as a 256-bit integer from the alloy library. Okay, so yeah, you can just kind of use that U8 or U256 from syntax kind of as a standard when you're doing stylus development. It usually just helps to work in alloy primitives a lot of times. It's easier than trying to convert back and forth from Rust primitives. So a lot of times by default, it just helps to just use those by default. Another type of value you'll need in your Rust in your smart contracts is the address type. That's an address in Ethereum is an account. It can also be a smart contract location. So addresses can contain ETH, and they can own tokens, and they can invoke other smart contracts and things like that. So just important to know, address could be a user account or it could be a smart contract. And then we're pulling that address type from the alloy library. And then I guess this example here, I'm creating an address from the 0x11. This is shorthand for what you see in the commented section for like, it's basically a 20 byte, it's 20 bytes of all ones. So that's just using a little bit slicker Rust syntax there. You don't have to know that necessarily, but it's one way to define an address using this address from 20 byte slice syntax there. All right, moving on to the types of variables. So these are the types of variables that you can use within the context of a smart contract. Okay, so you've got local variables, those are variables that are defined within a function body. Those are in-memory variables. They're purely exist in memory. Once the program once the contract has shut down, they're not stored anywhere. So that's just in-memory local variables. So right there in that gray box, you see let my var equals, that's defining a 32-bit integer with the value 123. The second statement there is state variables, which is, those are values that are permanently stored on chain. And those are stored in a database, and you can think of them as being stored in a database on chain. I'll show an example of that in the next slide, but think of them as database variables. It might help you if you're just getting started with this kind of thing. The other kind of variables, the global variables, those are variables that are provided by the VM itself. Okay, and those might be things like, you might see a reference to message sender or things like that that the VM is kind of injecting into the context of the smart contract. But there's many of those you can kind of look up on the docs to refer to them. But yeah, moving on to an example of like how you define state variables. So this is a contract struct, and I've got, if you notice here on the right, I've got I'm invoking a solidity storage macro, and below that I'm invoking an entry point macro, and then I'm declaring a struct called contract, and it's got 3 fields on it: initialized, owner, and max supply. Okay, to the right of each of those fields, you've got the types that those fields line up with, and these are storage types. So instead of using the primitive types that I explained before, I'm explicitly using these storage types, and that's necessary just to maintain this compatibility with Solidity, for example, to store things in a Solidity ABI compatible way. We have to use these special storage types that are part of the SDK. So you only use these types for database variables, essentially. So you're only using these for these state variables that are going to be permanently stored on chain. So you got a Boolean address. There's for every primitive, there is a storage type that lines up with that. So just something to keep in mind. You really just have to use that in the declaration, and you can think of this as like a database schema, more or less, when you use this style of a struct with the Solidity storage macro and then those storage types on the fields. Okay. Moving on. The Rust SDK, so to define an external method, okay, this is kind of like when you're writing a smart contract, you'll have certain methods that are exposed to the world. That means users or smart contract can invoke these methods. And in order to define these methods, and you can kind of think of them as your public API for your smart contract, use this external macro. And then on that impl below, notice it's got that impl syntax with the counter, which would be the name of the struct. So I'm impling for counter an external method called number, and that's that public function number, and it's returning a U256 from storage. It's calling self.number.get to return the number field from the storage struct that was defined. Like you could think this isn't the same struct, but if it had the number value on it, that's what this would be returning. And I'll show you that in detail in a second, because this is from the basic counter example that I'll show you. But it's important to note that in order for a method to be externally invocable by a user or smart contract, you have to use this external macro. And methods can either be read-only or they can mutate state. And there's just slightly different ways to define a mutable function versus a read-only function. All right, so with that, I'm going to move over to I'm going to open VS Code real quick to kind of go over the code real quick. Window, make sure VS Code. There we go. Okay. Can you guys see that? Looks like it's starting to work. Okay, cool. All right, so to kind of cover real briefly what you would do to get to this point, I'm gonna back out of this, and I'm going to like, let's say I'm in a folder, and you want to create, again, to get to this point, you want to do cargo stylus new. And then this one, I happen to make test 1, 2, 3, but I'm just gonna say whatever. Hello world, hello FOSSASIA. Let's do that. And so I'm just using the cargo stylus CLI, and I'm using that new command, and it's gonna create a full project. And if I cd into that hello FOSSASIA there. And then maybe I go to Vim real quick. Oop, and let's try to zoom in a little bit in case y'all can't see it too well. you know, it just created like a folder with a TOML file. That is, this TOML file is kind of like, you know, package.json and a JavaScript. You know, it's just kind of, it declares, you know, what libraries you need to use in your code. It might have things like your keywords of your repo, what version you're on, all this stuff. So that's something you don't have to worry about. It gets all set up for you. But if you go to source, that's where really the main thing to look at is. You might think that your code is in main.rs, but it's not. That file is mainly only used in these exports of a JSON API. You don't need to worry about that. lib.rs is what you want to focus on as you're learning. So if you're modifying the basic example, you kind of just like jump into lib.rs and kind of scroll down it. And actually, I'll pull back out of this, but just note that that's where it's at. So I'm gonna pull back out of them and go back to VS Code real quick, so I can kind of walk through. So right now I've got like lib.rs open on the basic counter example that gets created for you. Up here at the top, these are just purely dependencies. I'll just kind of call out this alloc dependency here. Just kind of for now, copy paste that from the existing examples if you're starting fresh. This is just a memory allocator, and you could kind of define your own or use your own, but by default, we use this mini alloc, which is very compact and uses very minimal space for like memory allocation. But these are kind of the more important ones to really kind of know. This is the stylus SDK dependencies. So I'm pulling in from the alloy primitives. I'm pulling in this U256, which is 256-bit integer from the alloy primitives library. And then I'm also pulling in this storage U256, which is what I just mentioned to you. In order to store a value permanently on-chain in the on-chain database, you need to use these storage types. All right. Below this is repeating what I showed you on that slide before. You got the solidity storage macro and this entry point macro, and I'm defining that. I'm annotating this counter struct with those. This entry point lets the stylus SDK know that this is the root of my database schema. There should only ever be one entry point struct defined. So this is the root of your database schema. Important to note. And then the solidity storage says that, okay, this every field in this struct should implement the storage type to make everything compatible with the stylus SDK. And it basically just lets the compiler know that if you try to use a field that is not a storage type, it'll bark at you. The compiler will let you know. So here we are using this U256 storage type. That means we've got this number field that we're going to store a value of, which is the basic counter value. So this is a simple counter contract. Its only function is sort of to like set a number, increment a number, and then fetch a number. So it's very, very simple contract to kind of understand. So we've got a single field storing a single number on that field, and then we're creating the external. So below this, now we're defining the external API for this contract. So we're using this external macro syntax with the hashtag, with the braces, and the keyword external, which is coming from the stylus SDK. And then we're defining on the counter, this impl for the counter. This is the same name as the struct above. So this is what kind of glues it together. We're implementing the counter, we're implementing external methods for the counter. So over here, every function, it needs to be public so that it's exposed to the outside world. We're defining the name. Here, we're just calling this is called the number function. It is getting a reference to self, which is a reference, a read-only reference to the storage values itself. From the counter struct, and then this method returns a U256. So it's just going to return a 256-bit integer. All right, and we're calling self.number.get. So in our stylus SDK, you kind of have to invoke this like get method in order to like fetch the value from storage and return it. And then like similarly for set, you call dot set and you pass it in. So it's just basic kind of getter setter syntax. It's important to note that like when you're working on chain, storage variables or state variables or database variables, they are the most expensive type of value to work with. So we kind of make it pretty explicit where when you have to invoke these getters and setters in order to retrieve or set values, so that you're not accidentally spending too much ETH or gas in order to set these values. So just something to keep in mind. This method below here is this is, so up here this is a read-only function, and we passed in this a reference to self. So this is an immutable reference to self, and this is a mutable reference to self. So that means we're allowed, if we use this and mute syntax, we're now allowed to mutate variables in storage. So that just kind of lets the compiler know, and it lets when we publish this to users know that this is a function that mutates state, and this is a read-only function. So that mute self is the self. It can be when you're defining a method. The first argument is always the self argument, that is a reference to the struct itself that this method is being defined on. Okay, so this is a mutable reference to the self, to the counter struct, and then we're passing in a new number. So if we want to, this method here just sets the number to some arbitrary number. So we're just passing in a new number, and we're setting the database value of self.number to that new number. The method below that simply increments it by 1. So it's a mutable method because it's getting a mutable self-reference, but there's no arguments needed because it just increments by 1. So right here it defines a local variable called number. It's just assigning the local number variable to the value from storage. So it's getting the current database value, and it's assigning that to the local variable number. And then it's going to set the database number. It's actually just going to invoke this method. So it's going to call self.setNumber, and it's going to say number plus 1. And again, look how it's using this U256 from 1 syntax. That's because this number is going to be, by default, because we're pulling it from storage, it's going to be an alloy type of primitive. It's not going to be just a Rust primitive. If we tried to say number plus just the number 1 without first saying, like if we tried to do this without first saying that it was without first converting this to an alloy type, in fact, it's the compiler is already warning us. It's saying cannot add basic Rust integers. So first we have to like convert it to the alloy type, and then we can add them together just fine. Okay, so just to kind of see this in action real quick, I'm going to use a utility that's called cast. And cast is a CLI tool that you can get it from getfoundry.sh. Unfortunately, I didn't include it on the instructions for FOSSASIA, but if you go to the website getfoundry, getfoundry.sh, you can download this program. It's a CLI tool that kind of helps when you're invoking smart contracts. Okay, Jason, you got a question. Go ahead, man.
Hey, Chris, go
ahead. Hey. Yes. You there?
Can you say my message?
Yeah, I can. Yeah, I'll wrap it up. I'm just gonna show the counterexample real quick, and then I'll wrap it up, and Jose can take it from there. Okay, let me just show like kind of the state real quick, and yeah, and then I'm sure you'll got a quick break before Jose starts, but I'm gonna just briefly show this in action, just to kind of show you how this works. The counter contract has already been deployed, and I'm just going to copy paste some commands here. Actually, let me real quick, let me see what the current value of the number is. So right here, I'm just using the CLI tool called cast. I'm passing in to my local dev node, private key. This is the address that the contract was deployed on. And I'm calling this number function. I'm expecting a 256-bit integer to be returned. If I hit call, it's saying that the current value of the counter is 28. Now, if I want to increment it, if I copy paste this, it's going to increment. It shows this like transaction hash and all these details. That means it executed on chain. And if I now call again the number function again, it should return 29. So incremented it by 1. This Foundry tool is a slick kind of tool for like working with smart contracts from the CLI. It's something I highly recommend, whether you're doing Solidity dev or Rust dev. Let me stop this real quick and let me go back over real quick to this. Just to finish, wrap it up. If you want that access to that tool, that Foundry tool, you can go to getfoundry.sh. That's this website down here. To reiterate, and Jose is going to go over this in more detail, but if you need any other help on any of this, you need to go to our docs website, docs.arbitrum.io. We also have a Telegram group at t.me/arbitrum_stylus. And then we have some example code that's available in our, if you go to github.com/offchainlabs, you can kind of type in stylus and you can see, you go to awesome stylus, you can see some examples there. There's also like a stylus by example website with some easy examples. But these are resources for you, and you can always ping us either in this Telegram group, on the Discord, or whatever to if you have any questions. And if you need me, I'm on Crisco2512 on Telegram or on Twitter. But yes, let me switch back over and stop presenting, and then I'll let, I guess there'll probably be a break, and I guess let Jason guide y'all from here. But thank you for your time, and I don't know if you have any questions or anything like that, feel free to ask them. I'll be here in the interim while Jose gets set up.
I'm going to continue to present on Arbitrum and Stylus. I'm going to build upon what Chris already mentioned before. So in this workshop, we're going to see an example of a smart contract written in Rust for an NFT. Okay. Well, first of all, my name is José Franco. I'm also an integration engineer at Offchain Labs. Here are my Twitter and Telegram handles in case you want to contact me. I don't write a lot on Twitter, but you can contact me there if you want. Okay. So I'm going to try to be brief on this workshop, but still I need to touch on several things. So in this case, we're going to talk about NFTs first. I'm assuming that some of you might know what an NFT is, some of you might not, so we are going to briefly explain what it is. We're going to explain, sorry, what is the ERC 721 standard that defines how to build NFTs, and then we are going to talk about how to translate that interface, that standard, into a Rust program, okay? So let's start with the basics. What is an NFT? So an NFT is it stands for non-fungible token. So they are different than the fungible tokens. Those are the ERC20 tokens. in that for ERC20, each token is not different from the others. It's the same one. Like, for example, if you have one USDC, which is a fungible token, it's the same as having another USDC. For non-fungible tokens, that's different, and each token is different from each other. Okay. So as examples, we have, for example, if this is used for art and collectibles. In this slide, we have some images of the Azuki collection. So this collection is an NFT, and each one of the images is a different token. So as you see, having the first token is different than the second one. And it can have different properties, different values. Yeah, they are completely different from each other. Okay. So NFTs are also used for gaming assets. So, for example, if you want to have a smart contract that has all the weapons that are used in a game, for example, each token might represent a different weapon with different attributes, with different properties, etc. And it's also used for financial instruments. That's another example. So, if you invest in a pool, you invest a pair of tokens in a pool, you can receive an NFT that identifies that investment, and actually that allows you to be like more liquid, because you can actually sell your operation to, I don't know, to a third party, to another person. So NFTs, as I said before, follow the ERC 721 standard, and that's what we are going to see to build our smart contract. Okay, but yeah, well, I'm going to touch briefly into these properties of an NFT. So no two tokens are the same. So there is some uniqueness going on in that in NFTs. Also, tokens can be divided into smaller parts. That means that you can't have like 0.1 NFT. You have to have at least one. And portability, we mentioned before, you can transfer that easily to other parties. And authenticity means that there is always track of who is the current owner and who has been an owner of a specific token or a specific NFT in the blockchain. Okay, that's actually a property of the blockchain more than the NFT, but in this context, it is very important. So the ERC 721 standard. This is like the guide to write our smart contract. And this is what we are going to use, right? So this standard defines an interface for APIs of NFT smart contracts. What does this mean? This means that it tells us what functions does our NFT have to be able to be properly like used in the blockchain, right? So it actually attempts to build a standardized way of operating with NFTs without having to know the implementation details. So you don't, as a user, you don't really need to know what is inside a function to be able to use it. I mean, you should know from a security point of view, but as a user, just use it. You don't know like how it is implemented. You don't know actually what language it is implemented in. You just need to know the signature of the function to be able to call it. And that's what the standard gives us. It doesn't give us implementation details, sorry. It just gives us function signature. Okay, we're going to see that now. This is an example, well, not an example. This is part of the actual ERC 721 standard. Here we have several function signatures, and this is what the standard tells us. So if we want our token to be transferred in a standard way, we have to implement a function called transfer from that takes these arguments and, well, in this case, doesn't return anything. But for example, the balance of function takes one argument, the owner, and returns a UIN 256. So the standard does this with all the functions that the NFT should have as a minimum. You can have more functions if you want, but as a minimum to be standard, you should have these functions with these signatures, okay? And the standard also gives us signatures for the events that this smart contract, this NFT has to meet, okay? We're going to talk about events soon, and you'll understand why they are important. Well, you have the full specification here if you want. Don't worry about copying any of the links because I'm going to share these. Well, I'm going to share later a QR code that goes to a repository of code that we're going to see today, and that has all the resources that we're going to talk about today, including this presentation. I'm also going to share these in the FOSSASIA specific Telegram group. I think there is a banner in the workshop room with that QR code that you can scan as well if you want. So yeah, I'll share that later in the group. My colleague Chris already explained this, but these are just some resources to start with Stylus. There is a quick start in the public documentation of Arbitrum that goes through how to set up your environment. Chris already explained all this, so I'm not going to get into details about this. There's also this Stylus by example portal that gives a lot of examples of how to use Rust to write your smart contract and do several specific things for Stylus, like for example, how do you emit a law in your smart contract, and many other things. And the awesome Stylus repository that has a lot of examples, a lot of resources to keep exploring Stylus and more examples. This is also, well, something that Chris already explained, how to create a new Stylus project, so I'm not going to get into that. Just the kind of Stylus tool. It is also explained in the public documentation, so in case you missed the previous workshop, it is explained there. All right, so let's explain a bit what do we need to keep in mind when creating our Stylus smart contract. So I like to think about 4 different elements that I need to keep in mind. I need to think about when adding functionality to smart contract. And this is actually the elements that we are going to touch on the different functions that we want to add for our element. All right. So the first one is the storage layout. That means what information we need to store in the smart contract and what type of information that is. Okay. Then we need the implementation of the methods. Obviously, what method we need to have and how they are implemented. We need to know also the events that we are going to emit, and we have to define them in our smart contract and emit them in the methods that we are going to emit them. And we need to keep also in mind error handling. Okay, we're going to see all of these with the examples that we're going to see today, except error handling. I'm not going to cover that, but there is plenty in the example repository that I'm going to share. There are many examples as well in the documentation. So yeah, that's on the next one. So a storage layout, first thing. Following up on what Chris explained already, with the first thing that I like to think about is what variables do I need to store to be able to give the smart contract the functionality that I want to give it, and also what variables do we need and where do we store them, right? Where do we put them in the code, right? So we have these macros, solidity storage and sol storage, that allows us to do that, right? So we just use that macro. We can use solidity storage if we want to write this struct in using Rust syntax, or we can use sol storage if we want to use solidity syntax. So in this case, for simplicity, we are going to use solidity. And inside the struct that we are going to create, we are just going to add whatever storage variable that we need, right? So in this case, it's a mapping of token IDs to owners. If you don't know what a mapping is, think of it as similar to an array. There are arrays as well in Solidity, but you can picture it like an array where the u into 56 is the key of the array and address is the value. So we are saying for each token ID, who is the owner, what is the address of the owner, okay? And we are storing that in the owner's variable. So next is the implementation of methods. As Chris already explained, we use this impl keyword followed by the name of the struct that we declared on the storage part, and then we just implement, define the methods that we want and implement their code there. Okay. Events. Events are, for those who don't know what an event is they are signals that the smart contract emits when certain actions are performed. Okay. So, for example, if you are transferring a token, an NFT, a specific NFT, from one user to another user, the smart contract emits an event saying that, okay, this NFT has been transferred from this address to that address. Okay. So those are used, for example, by front ends, user interfaces that want to notify users when something happens in the blockchain, or I don't know, if a user wants to track what happens in a specific smart contract, he can just keep track of the events that are emitted there. Okay, so the standard, the ERC-721 standard, gives us some events that need to be emitted, and yeah, we're going to use them here. This is an example of an event. The standard, sorry, gives us this event signature, and this is how we add it to our Rust code. We just use the same signature inside the sol exclamation mark macro. Okay. Okay, so we are now going to see the specific methods that we need to implement. This QR code points to this repository where the actual code of the project that of the NFT actually exists. I'm going to try to be very explicit about the examples. I'm going to show like the code that we need to implement the methods and define the storage variables that we need. But if you want to follow along with the code, you can scan this QR code and just following in that code, okay? So in that project, there's an SRC folder. Inside, you have two files. There's a lib.rs file and an ERC-721 file. Most of the functions that we're going to see are in the ERC-721 file because that's the actual implementation of the standard. And the lib file is just importing the interface to create the NFT, all right? You don't need to have it, but if you want to follow along, just scan it. All right, so what do we actually need to build our NFT? We need two properties, a name for our NFT and a symbol, and we need several methods. We need a transfer method, an approve, minting NFT, burning NFT, and a token URI, okay? So for the properties, yeah, we just need the name and the symbol. Name can be a full name of the token, for example, Stylus NFT, and the symbol just an abbreviation of that token, SNFT, for example. And we are going to use these variables to store that information in the contract, right? So inside the public struct, we are going to just use a string name and a string called symbol, and that's it. We are going to store the variables there, okay? And the methods, in this case, we are assuming that the name and the symbol are hard-coded in the contract. So we are just going to create two getters for those variables, okay? So we just create one name function that just returns the name that we stored in the variable, and the symbol function that just returns the symbol that we stored in the storage variable. Okay, if we want to change that information after the contract is deployed, we will need setters for that. We're going to see examples of setters later, but for now, just the getters. All right, and now one of the main parts of the NFT, one of the most important parts, how to transfer the token. Okay. So the transfer function allows us to, transfer functions, because there are several, allows us to transfer a token from one account to another. So when implementing this functionality, I I always like to think, okay, what do I need to keep track of to give this functionality to the contract? And there are two things that I need to keep track of. What's the balance of each user? So how many tokens does a certain user has? And who owns what token at any given time, okay? So, yeah, and also the ERC 721 standard gives us these signatures for the functions. One transfer from function that just takes 3 inputs from a to and a token ID. So this function, what it does, it just takes this token ID and transfers it from the from address to the to address. And 2 safe transfer from that actually do the same, but if the to address is a smart contract, it will execute a special function in that smart contract. Okay, we are not going to get into details about this, but just so you know that there are 3 transfer functions. The standard also gives us one event that needs to be emitted when transferring a token, and that's the event transfer that, well, emits, logs the 3 information that we need, the 3 pieces of information that we need: the from address, the to address, and the token ID. Okay. Now, let's go into Rust. Now, let's go into our contract. So, how do we store the information that we need to keep track of? We use 2 mappings for that. One mapping that we saw before, actually, the owner's mapping, that maps for each token ID who is the owner, and then a balance map. So for each address, how many tokens do they have? With these 2 mappings, we can keep track of everything that we need to keep track of. And for the methods, we are going to see the transfer from method, which is the first method that the standard tells us to implement. So for the transfer from, the standard tells us we need a from, a to, and a token ID. And in this case, we have divided the execution into 2 internal functions. The first one is require authorized to spend, and this is basically going to check if the user who is calling this function is authorized to transfer that token. So for example, if I have 1 token, well, another person shouldn't be able to transfer that token on my behalf, right? So we are going to take a look at this function in the next section when we talk about approving an NFT. But for now, just know that this checks if the user who is calling the function is authorized to send that token. Okay, and then we call this internal transfer function that we are going to see now. So the transfer function takes the same 3 arguments, and what it does is that it's going to create a mutable variable for the owner of the token. So at first, the owner will be the current owner of the token that we want to transfer. So we did this little check here to verify that that actually that token has that NFT, and then we modify the owner to the destination address. All right. Then the next thing that we do is that we modify the balances of the from address and the to address, from the source address to the destination address. From the source address, we decrement 1 from their balance, and from the destination address, we increment in 1 their balance. Okay. And finally, we emit the log that we need to emit. Okay, the safe transfer from functions, we are not going to see their details, but they basically do the same as transfer from, but call the function on ERC 721 received on the destination address, in case those are smart contracts. All right, so second important part of an NFT, approve the management of an NFT. Okay, so these functions, what they do is that they grant another account the ability to manage 1 specific token ID or all the tokens owned by a specific account. Okay, so for example, if I have an NFT, I can give another person the ability to manage that token ID for me. And manage in this case means they can transfer that token from me. So why would I do that, for example? Well, if I'm using a platform where I can buy and sell NFTs, I probably want to give the ability to give that platform the ability to move my tokens so they can match buying and selling operations, right? And move those tokens on my behalf. So that's one example. For example, there are many others. So what do we need to keep track of in this case? We need to know what accounts have been granted rights over specific token IDs and what accounts have been granted rights over all tokens that are owned by specific accounts, okay? So these are the functions that the standard tells us that we need to implement. We have an approve method where we say, okay, for this address, I want to give this address the ability to manage this token ID that I own, obviously. And set approval for all is like, says something like, I want to give this address the ability to manage all my tokens. And I can enable that or disable that with the second parameter. So I can first enable the ability to move all my tokens or disable that later if I don't want to keep that on, okay? And then we have two getters for the same thing, for a specific token ID and for all the tokens of an owner. Also, the standard tells us to emit two events, one for when we grant allowance of a specific token with the event approval, and one when we grant allowance for all the tokens that I own, that is approval for all, right? So, okay, let's move to Rust now. How do we keep track of that? What storage variables do we need? So we need two. We need one for the approvals of a specific token ID. So that's a map from token ID and who can transfer that token on my behalf. And we need a mapping, another mapping for addresses. I mean, this address is for all my tokens. I want to give the ability to move all my tokens to this address, okay? And I can enable or disable that. That's more or less what it says, right? So for the methods, we need one for approving, the approve method that we saw before. So we take the owner of the token ID. We verify that the user who is calling the function is either the owner or can manage the tokens of that owner. Remember that MSG sender, well, remember, I don't know if you know that, but MSG sender references the user who is calling the function. So MSG sender, if I'm calling the function, that will be my address, okay? So if my address is not the owner of the token, or the owner of the token hasn't granted me the ability to move their tokens, then I can't perform this operation, okay? This throws an error. So if everything is okay, then a new entry is added to the approved mapping that we saw before, and a log is emitted. For the set approval for all, it's the same operation. Here, only the owner, only I can grant someone else the ability to move my tokens, okay? So I am the only one who can call this method, and, well, not the only one, but when I call this method, it's going to create an entry for my address, okay? And also emit a log there. We have the getters here for the two mappings, get approved and is approved for all. I'm moving a bit too fast into these. These examples are all in the code, in the repository, so you can take a closer look later, but as we have short time here, I'm just moving fast through them, okay? And then the function that we left before without checking, which was require authorized to spend. Remember that when we want to transfer a token, we first check if the user who is calling the function is able to move that token, either because he's the owner of that token or he has been granted approval of moving that token. All right. So this is what this function does. So we first get who is the owner of the token. and we check obviously that the owner has that token. And then if the owner is the caller of the function, then we return okay. That means that they are authorized to spend. We check in the approved for all mapping if the caller of the function is able to manage all the tokens of the owner of that token. Then we return okay. We say okay, you are approved to spend. And then we check the specific approved mapping to see if this specific token ID can be managed by the message sender, by the caller of the function. Okay. And if none of these conditions are met, then we throw an error, meaning that the caller of the function is not allowed to transfer this token or to manage this token. Okay, so that's transfer and that's approval. For minting, I'm going to explain, just minting and with the scripts. So minting, in this case, there is no specific interface in the ERC 721 standard that tells us, okay, you have to create this function to mint, because it gives us the ability to say, okay, you can create all the tokens at the beginning when you deploy the contract or not, or you can have a function to mint the token and have it have the users pay some money to mint a token. But basically minting a token, what it's going to do is it's going to create a new token, okay? So for this function, for this functionality, we are going to create this function mint. We've added the payable keyword here, but for this example, it's going to be free to mint. And what we need to keep track of is how many tokens have been minted, and what a specific token is going to be created next, okay? And we're going to see why now. So for the storage, the only thing that we need is the total supply. We need to keep track of how many tokens have been minted. And this is also important because in this example, and this also happens in many NFTs, we are going to create the tokens incrementally. That means that when we deploy the contract, so no tokens are created, the first one that is going to be created is the token ID 0. Then the next one is going to be the 1, next one is going to be 2, next one is going to be 3, and so on and so forth. So for the method, we are just going to create this mint function. The token ID that we are going to create is actually the total supply. That means that, well, as I said before, when we deploy the contract, the total supply is 0. So the token ID that we're going to create is 0. When we create that one, the total supply is 1. So the next one is going to be the token ID 1, so on and so forth. So we get the token ID, and then we increment the total supply in 1. Okay, and then we call the transfer function that we saw before to transfer that new token ID from the default address, I'll explain this now, to the MSG sender, who is the caller of the function. So why do we send that from the default address? Well, this is a particular behavior of blockchain, actually. That means that when we deploy the contract, we say that no tokens exist, but technically all tokens are owned by the 0 address. So all tokens are owned by the 0 address. So when we create a new token, we transfer that from the 0 address to the caller of the function in this case. Okay. And we also need two getters, which are the balance of, that gets a specific entry in the balance mapping that we saw at the beginning, and the owner of that, it does the same. It gets a specific entry of the owner's mapping that we saw at the beginning. I'm not going to explain burn an NFT because we don't have a lot of time, but basically it does the opposite of creating an NFT. It just removes a token without decrementing the total supply. It just sends the token to the default address, to the 0 address. Okay. All right. Token URI. let me briefly explain this. This is not actually part of the ERC 721 core standard. It's part of an extension of that standard. And what it does is that associate a specific URI to every token, so we can store specific information somewhere else. That can be on chain, off chain, whatever. So, and that information usually is, well, the name of that specific token, the description of that specific token, properties that that specific token has that might be different from other tokens, and yeah, several other information that we can save there. And and in this case, we can do like several different implementations of this, but one basic implementation will be just to return a root URL with the token ID .json file that will return, well, the structure, the information of that specific token. Okay. All right. So before finishing, let me briefly talk about how to call these methods. And Chris already touched a bit into Foundry. Sorry, that we can use Foundry to call these functions. And I wanted to show you an example here, because you saw that, I think I can show you an exact, yeah, I can show you an example here. If we go to the balance of, for example. So as you see here, so we declare this function, this balance of function, and as Chris mentioned, we use a snake case to call this function. But when we want to call this contract after it's been deployed, we are going to use a regular ABI like Solidity does, like we do with Solidity contracts. Okay, so if we go to, in this repo, also this is the one that I'm sharing, there is a scripts folder to perform all these operations individually. Okay, so if we go to the get balance, we're going to call that same function using camel case as we see here. So this is because Stylus wants to, well, not Stylus actually, is to be able to guarantee to the user that they don't need to know the implementation details of any contract. We need to provide the same interface to access those contracts, regardless of the language they are written in. So if they are written in Solidity, they are accessed in this way. If they are written in Rust, they need to be accessed the same way. Okay, so that's why Stylus modifies, well, in this case, the SK modifies those snake case functions to be called using camel case or the standard way that we call smart contract functions. Okay, so this is just one example of Foundry that I think Chris wanted to touch a bit upon. We used cast call. We pass here the RPC URL. This little variable that we have here is preloaded with the URL that we are using. In this case can be your local node, can be Stylus testnet, for example. And then we pass the contract address that we want to call. This will be the contract where the contract is deployed. The address where the contract is deployed, and then the function that we want to call, the inputs that it receives, the outputs it returns, and well, in this case, you put the inputs of the call that you're going to make after the signature of the function. Okay. Jason, if you can tell me how much time I have left. If I don't have any more left, just tell me so. So if so, I can touch a bit on other things. But basically, yeah, that's a bit what I wanted to show you today. There are still a lot of things that could be explored here. In this QR code, it's the same one as before. This is the repo of the NFT contract that we just talked about. We have here several resources. I'm going to share this presentation as well with you. That's going to be inside the repo. And I think that's it. Yeah. Let me know, Jason, or anyone, if I still have some time left. If not, we can finish here. Okay, so while they respond, I'm going to show you something else. So in this repo, this is the repo that I'm sharing with you. This is the NFT contract. So we have several scripts, right? So you can add here several the variables that you want to use for this script. If you have used Bash before, or any terminal, this is usually the same with any shell. You can create here define the different variables that you want to use, and then you can call the different scripts that are inside this folder. So you can see what happens when you perform certain operation and what instruction you are using, what CLI command you're using for that specific instruction. Okay. So in this case, if we want to deploy our contract, for example, we will just call script deploy. Also, all these instructions that I'm sharing here are available in the README of the repo. Okay, so yeah, if you can read that from there as well. This deploy command, what it does is just it deploys. In this case, it deploys to the stylus testnet, and it gives us the address of the contract that's been deployed. Right. So in this case, it is our NFT. So if we want to, for example, check the balance of our address, we can just call this command right here, and we see that the NFT balance is 0, and we can mint. You can call the mint. We can call the mint script to mint 1 token. Okay. This is sending the transaction to the blockchain now, to Stylus testnet. Right, perfect. If we check the balance now again, we have 1 NFT, and yeah, we can also transfer it to another account. We can get the token URI if we want. For example, this is prepare. These are all commands that I have prepared here to do operations with basic contract with predefined variables. For example, in this case, we're going to get the token URI of the token ID 0 here. Do that. We get that the token URI is this one, and yeah, I think that should be all. If you have any questions about Stylus, you can go to our Arbitrum Discord. There's a specific Stylus channel there. You can ask those questions there. I'll be sharing these. There's also a Telegram group. We have all of it here. This is specific for Arbitrum Stylus. There is another specific for FOSSASIA. Will be around there as well. And yeah, I think that's all. Yeah, Jason, I'm done. So thank you very much for being here, and yeah, hope you enjoy the rest of the day. Thank you.
Hello. All right, that wraps it up. Thank you very much, Jose. Really appreciate it. I don't know, it must be an ungodly hour for you. So really appreciate you taking the time. The auditorium is quite full of people, so really appreciate that. Okay, I think that wraps it up for us. Well, unless either anyone who wants to ask Jose a question before he gets off. All right, if not, yeah, just thank you very much. I know it was a very long day, must be tired. So yeah, just I think we gave you all the links and everything for you to download and come check it out. But please, Jason and I will stick around for maybe 15 minutes or so to answer any questions. If not, I think all the information is on online. And please follow us on Twitter, and then also please join us on Telegram. Thank you very much. Have a nice day.